For 10 videos, we have been building up to this moment. We understand the architecture, we understand training at scale. Now we move from building AI to using AI live. This is where the theory meets reality, where ChatGPT actually speaks, where Cloud A actually responds, where all the training turns into text you can read. Have you ever wondered why same prompt gives different answer? Or why sometimes AI sounds creative and sometimes it sounds robotic? Or what temperature actually means when people talk about it? Here's our question for this video. After training is done, how does an LLM actually produce an answer when you type something? That process has a name. It's called inference. And understanding inference is the key of using these tools effectively. When you type a prompt into ChatGPT, what actually happens? Let's look at those steps. Step 1, your text gets converted into token. This is the piece we talked about in our last video. Those tokens run through the transformer layer, all the attention and feed forward processing that we talked. Step 3, the model predicts the probability of every possible next token. Not one answer, but a whole distribution. This is very important. Step 4, it selects one token based on all those probabilities. Step 5, the tokens get added to the output and the whole process repeat from step 2. You can look at the cycle that is animated on the screen right now. This loop runs hundreds or thousands of times for single response. Here is a mental model that you can keep in your mind. Your phone's autocomplete predict the next token based on what you type. LLM do the same thing, but at a scale that produce entire coherent paragraph. Same basic principles, massive difference in the level. Let's actually watch text generate. Look at the demo screen. The blue token are your prompt. Explain quantum computing. Now I hit generate response and watch what happens. See how each green token appears one at a time? The model generate quantum, add it to the context, generates computing, add that, generates uses, and so on. Each token is predicted based on everything that came before. This is important. The model doesn't think about the whole answer first, then type it out. It generates one token, see what it generated, and that influences the next token. The response emerges incrementally, not all at once. Here's something that changes how you think about AI. The model doesn't output a word directly, it outputs a probability distribution over all possible tokens. Look at this example. The cat sat on the model doesn't say the next word is Matt. It says Matt has probability 45%, floor has 28%, and bed has 15%, table has 8%, ceiling has 4%. Now, from this distribution, how does the model select the next token? If I say select the next token, it has selected table, again bed, again floor. See what happened? Now we have a problem. We got probabilities, but we need to pick one token. Should we always pick the highest, that is Matt in this case? That would be predictable, right? But boring and repetitive. Should we pick randomly? That might Select ceiling, which makes no sense for a cat. The answer lies in the sampling strategies. Temperature is the most important sampling control, and it is one you will encounter most often. It controls how much randomness the model uses. If we drag this slider, let's say towards 0.1, at low temperature around 0.1 or 0.2, the model almost always pick the most likely token, very predictable, very factual, and sometimes repetitive. You can look here, right? The cat sat on the mat, the cat sat on the mat, the cat is common household pet. At medium temperature, that is between around 0.5 to 0.9, you get a balance. Natural conversation with some variety. The cat sat comfortably on warm mat, watching the birds outside with curious eyes. At high temperature, 0.9 and above, the model considers less likely tokens more seriously, more creative and more surprising, but sometimes nonsensical. The cosmic feline preached upon the eternal tapestry, contemplating quantum uncertainty of existence. Wow. Low temperature more or less is used for factual tasks, code generation, data extraction, anything where you want consistency. Medium for general conversation. High for creative writing, brainstorming, when you want the model to surprise you. Think of it like coffee. Low temperature is mild coffee, controlled, predictable, won't surprise you. High temperature is strong espresso, intense, unpredictable, might wake you up or might overwhelm you. Same beans, different brew. Temperature doesn't change what model knows. It changes how it selects from what it knows. Temperature isn't the only control. There's a top K is another important one. Instead of considering all possible token, you only consider the K most likely one. Look at the visualization. We are predicting what comes after the scientists discovered. The tokens are ranked by probability with K equal to 5. Only top 5 tokens are green. Those are the candidate. Everything else is gray. It's excluded entirely. If we change the value, let's say we make it 3, watch, only 3 candidate. Let's say if we make it 8, all tokens are the candidate. Top K removes weird unlikely words that could derail the response. If there are some rare token with 0.1% probability that makes no sense, top K exclude it completely. It's like limiting a brainstorm to the best ideas rather than letting every random thought in. Top P is even more smarter. Instead of fixed number of token, you pick enough token to cover P% of the probability mass. Look at the two example. On left, the capital of France is, the model is very confident Paris has 92% probability by itself. With P equal to 0.9, you only need one token. On the right, I really enjoy, many things are plausible, right? Reading 18%, cooking 16%, music 14%, and so on. With P equal to 0.9, you need 7 token to reach that threshold. That is why top P is so popular in production system. It adopts automatically. When the model is confident, it consider few options. When uncertain, it consider many. Most system set P around 0.92 or 0.95. It's more natural than a fixed K. Here's something every ChatGPT user has noticed. Ask the same question twice, you often get different answer. Now you understand why. 3 reasons. First, probabilistic sampling. Unless temperature is exactly zero, there's randomness in selection. Different runs can pick different tokens even with same probabilities. Second, context sensitivity. Small variation early compounds into bigger difference later. If the model picked quickly instead of fast in the first sentence, that change every prediction that follows. Third, hidden randomness. Even at temperature zero, floating point arithmetic and system variation can cause subtle differences. Here's a mental model to think about this. A jazz musician plays the same melody differently each time. Same structure, different expression. LLM inference is structured randomness. The learned pattern provide the structure, but each performance is unique. That's not a bug, it's a feature. It makes the model feel more natural and less robotic. Now that you understand inference, you can understand why hallucination happens. Inference asks, given this context, what token is statistically likely to come next? It doesn't ask, is this statement actually true in the real world? If the prompt implies fact that doesn't exist, or if the context is not well defined, the model fill gaps probabilistically. It predict what text should come like based on pattern. Yeah, even if that text describe things that don't exist. The model feel confident because the pattern fits, not because the fact is verified. And here's the fundamental issue. Training teaches patterns from text and inference continues those patterns. Neither phase checks whether the output correspond to reality. Techniques like retrieval augmentation helps pulling in real document before generating, but a core issue remains. Understanding this helps you use these tools wisely. Okay, let's verify that everything has connected. During inference, an LLM repeatedly predicts the next token using probability distribution with sampling method like temperature and top P shaping the final output. Let's unpack this with me. Inference is the process of generating output. It happens token by token. Each token is selected from a probability distribution. Temperature controls what? Randomness. Top P controls how many candidate can compete. All of this shapes the final text you read. If that sentence make sense to you now, you understand the real-time AI generation. You know what's happening between pressing enter and seeing the text appear. Now you understand training and inference, how models are built and how they generate output. But here is a practical question. How do you actually talk to these models effectively? That's the next video. We cover prompt engineering, prompt structure, system versus user prompt, chain of thought, few shots example. This is practical superpower that make all technical knowledge that we have acquired actually useful. Next time when someone asks you why ChatGPT gave you a different answer today than what you got yesterday, you know exactly why, right? That is temperature, sampling, and beautiful randomness of inference.